Hello everyone! In this video we will continue to examine topic 5.1 electric fields, and in particular focusing on charge and electrostatics. So, in the last couple of videos we examined the model of charge, and we're going to begin to consider the following question, which is how does charge move or transfer? How does it go from object to object? How does it move within objects? And the big picture answer in this case is that the charge carriers, that is the particles or objects, depending on whatever they are, that carry the charge, depend on the material. So what actually is moving, what is transferring charge, depends on the material that the charge is flowing in. And in fact, most of you have already seen these terms, but we have two general pieces of terminology for objects that allow charge to move easily and objects that do not. Insulators is our vocabulary word for materials through which charge does not move easily. Plastics tend to be good examples of insulators, as is air, depending on the circumstance. And in an insulator, the electrons are tightly bound to the molecules, either in the plastic itself or, in the case of air, to the molecules of oxygen and CO2 and nitrogen. They stay put once they're transferred. So if you do manage to transfer electrons, which is not impossible, they more or less stay where they are unless they're discharged in some way. And it is important to note, though, that electrons inside those molecules can reorient to produce a net separation or polarization, as discussed in the last video. But they're bound to the vicinity of those protons. They have to stay nearby because of the forces between them and the protons. Conductors, on the other hand, are materials through which charge moves easily. So solids, we typically think of metals like copper and gold. As you may have examined in chemistry, metallic bonding is such that the protons in a metal exist in an ionic lattice. So they are sort of evenly spaced apart at particular points, and then the electrons are not necessarily bound to a particular ion, but sort of float around in what is traditionally referred to informally as the sea of electrons. This is not the case if you melt the metal, if that metal is molten. So then you have those protons moving freely as well, but otherwise the charge carriers are those electrons in the sea of electrons. And in salt solutions, in sort of water with various kinds of salt, the positive and negative ions that are dissolved in the solution, like positive sodium and negative chloride ions, can move freely. And in a salt solution like this, both the positive ions and the negative ions can transfer and move and therefore conduct. It's important to note that insulators and conductors are really a spectrum, and a pretty broad one at that. So people, for example, are conductors compared to plastics. You know, we're much better conductors than a piece of plastic, or air for that matter. That's why you are more likely to be hit by lightning standing out in the field than the air next to you is. But we are insulators compared to something like a metal. Okay, so if lightning hits a car that we're in, for example, or a building that we're in, that lightning, that electricity, and that charge will travel along the outside of the building along the metal. Because metal is a much better conductor than we are. So insulators and conductors are two general categories that describe whether charge can move freely through them or not, but it is a spectrum. We are somewhere in the middle. So is wood, for example. All right. traditionally at this point, we would conduct some very practical experiments using something called an electroscope. And what I'm going to do in the rest of this video today is to simply discuss those experiments and use a little bit of a simulation to kind of show what's going on. Ideally, you will also see these in person. So these experiments are done, again, using our cloth and our plastic rod. But the cloth rubbed on the plastic rod is then brought near something called an electroscope. And in this case, a gold leaf electroscope. And what an electroscope does is it allows you to sort of detect the strength of charges in particular ways. And we're going to see sort of how that works. So let's say you rub a cloth on a plastic rod and you bring it near this device. This device contains, this electroscope contains a metal cap on the top, an insulated sort of container, okay? So an insulated container, insulated from the ground and the rest of the environment so that no charge can pass in or out. It then has a very, very, very thin gold leaf, okay? A very thin gold leaf, a very thin piece of foil that is attached to the metal stem. So in a gold leaf electroscope, you have a metal stem and then a gold leaf, at least one of them, and a metal cap that it's attached to, okay? What happens, well, there are a number of experiments that you can do, but if you rub cloth on a plastic rod, you transfer extra electrons to that plastic rod, so now that plastic rod has a net negative charge. You then bring it close to the cap, and what you'll see is that that gold leaf rises up. Okay, so the gold leaf rises up. It's pretty distinct. And why is that happening? Okay, well, that can be explained using everything we already know. So you have a net negative charge on that plastic rod. When that plastic rod is brought near the cap, the electrons that are in the cap, which are in the sea of electrons, because that metal cap is a conductor, can move. They feel repelled from the electrons in the plastic rod, and so they sort of retreat down into the stem. So you get extra electrons in the stem and the leaf compared to the cap. This is basically a case of induced polarization, just as with the wall and with the paper. The electroscope is still net neutral, but the cap now has a surplus or extra protons compared to electrons, and the leaf and the stem have a surplus of electrons. They have extra electrons, and the extra electrons in the leaf and the extra electrons in the stem repel each other. The leaf is very light, and so it is repelled upwards. So you can see that pretty distinctly. So let's take a look at what that looks like in a simulation. Okay, so in this case, we're going to have a negatively charged rod, and we're going to bring that rod close to the electroscope. We can see that as we bring that rod close, the electrons are repelled from that metal cap down into the stem, and in this case, this electroscope is shown with sort of two leaves, and those leaves are repelled from one another because there are extra electrons in those leaves, and they repel each other. Notice that if I bring the rod back away, the electrons return to where they were before, and we can see very clearly that the electroscope is net neutral. In the next experiment, we do the same kind of setup. So we rub the cloth on the plastic rod, and then we do something a little more direct, which is we touch the electroscope. Okay, this involves sort of taking the rod and scraping it along the top of the metal cap in person. And when it gets close enough, you will actually hear in person sort of a tiny little zap, little case of static electricity as that charge jumps to the metal cap. Because when that negatively charged rod gets close to the metal cap, the electrons are attracted to the extra protons in the cap. Remember, the other electrons have retreated down into the leaf and stem. Those electrons then jump to the cap and stem system. And if you take that rod away, that cap and stem now have extra electrons. And as a result, the leaf is repelled, and it stays repelled, even if that rod is brought away. Okay, even if that rod is brought away, because the entire electroscope then has a net negative charge. There are extra electrons on the whole thing. Now, to get rid of them, we can do something called grounding the electroscope. Okay, and that's where we connect that insulated metal piece consisting of the cap, the leaf, and the stem to the ground. We can do that pretty straightforwardly simply by touching it. Okay, by touching it. That grounds the electroscope. The electrons feel repelled from each other, and so they are pushed up into sort of the person touching the metal cap, and they retreat until that metal piece in the electroscope, until the electroscope itself is net neutral. Our final experiment to discuss is a case of charging the electroscope by induction. So it turns out we just discussed a way to sort of create this appearance of charge where we induce polarization in the electroscope, and we discussed a way to transfer charge directly from the plastic rod. This produces a negatively charged electroscope. You can actually produce a positively charged electroscope as well. And here's how you do it. You're going to take that negatively charged rod, and at the same time, you're going to ground the electroscope. So another person or sort of another hand is grounding the electroscope at the same time. When that rod is brought near, those electrons in the rod repel the electrons in the electroscope. But now the electrons in the electroscope don't have to retreat down into the leaf and the stem. They have another path. They have another place to go. Those electrons then retreat into the person. The person then takes their finger away at the same time that the rod is brought away, and what you are left with is net positive charge on the electroscope. Let's take a look at that. So we ground the electroscope first. That touches the electroscope here, or the person is touching the electroscope. We bring the negatively charged rod close, and we can see those electrons are repelled into the person. Notice that at this point, the leaves on the electron are still down. The leaves on the electroscope are still down. We then take the hand away, unground it, take the rod away, and now we see that there's a net positive charge on the electroscope, and those leaves feel repelled. Notice that if I bring the negatively charged electroscope back close, I can get those leaves actually to drop by repelling electrons back down into the leaf and stem and neutralizing the leaf and stem. Okay? Notice that if I come at the electroscope with a positively charged rod, I can bring that rod close and actually attract electrons even more up into the cap, producing more deflection in the electroscope itself. This process of producing a charge on the electroscope without touching it with the charged rod itself and without directly transferring charges is called charging by induction. And it works by inducing polarization in the metal components of the electroscope and then grounding it so that the extra charge can be repelled into the ground. Notice there's a charge on this electroscope now, and I can resolve that charge or neutralize that charge by grounding it directly. So electrons come from this sort of infinite source of electrons. Infinite is in quotes, but very, very large source of electrons in the person, and that neutralizes the electroscope.